On Sunday?
That's true, yeah.
Okay, so let's chit chat about the lab. Okay? So this is kind of the culminating thing of where we are at right now. So the first thing we figured out was how to do physics. What do we measure? What units are we going to use? That type of thing. Then we said, okay, let's roll that into velocity. Okay, what's velocity? That's your rate of change in your position. Well, what does position mean? Oh, where were you at in the frame of reference? That type of thing. And now we're going to look at acceleration, which is the rate at which your velocity changes. Okay? And again, I cannot emphasize this enough. You have to get out of your mind that when I'm talking about acceleration, I'm talking about speeding up. Okay? That's not what I'm talking about. Okay? I might be. Okay? But acceleration could also be slowing down. Okay? Acceleration could be changing direction. So if you have a certain velocity vector, and you look at that vector at some point in time later, and it has changed in any way, shape, or form, gotten bigger, gotten smaller, changed the direction of it. The only way that's going to happen is if the force acts upon it, because Mother Nature is a hookah-smoking, tie-dyed, gray-haired, laid-back old woman who is just chilled, and she's a lazy prima donna, and she's not going to change anything unless you make it. Okay? So Mother Nature says, you got a velocity vector? That's cool. You can keep that velocity vector. You want to change it, that's going to require force, because I'm not going to do it on my own. So here's the fundamental idea. You gave that cart a push, okay? You established some initial velocity. Call that V1. And it's I'm going to point that up the ramp, because that's the direction that it's going. If I threw it straight up in the air, I would draw my vectors pointing up. If I throw it down, I would throw it down. That's the direction my velocity vectors would point. So we're just going to call this V1. Now, at some point as this thing is going up, you're going to look at it at a second velocity vector. One of three things can happen. The velocity vector has gotten bigger, the velocity vector has gotten smaller, or the velocity vector has stayed the same. That's it. Okay? Those are the only three options. It's a dime. I gave this thing some initial velocity. What happened to that velocity vector as it went up the ramp? It's going to get smaller. So I'm going to draw V2, something like this. Okay? Then I'm going to draw V3, something like this. Okay? If you want me to think these vectors are getting smaller, you draw them so these 56-year-old eyes can look at them and go, oh, they're getting smaller. Okay? Now, as soon as you realize that it's accelerating, now you have one of two choices. Either your acceleration vectors point in the same direction, or they point in the opposite direction. That's it. That's it. Either point in the same direction or the opposite direction. Okay? So, which direction are they going to point? Up or down? Down. Okay? So, my acceleration vector is going to point down the hill. So, I'm going to have some negative acceleration. So, call this negative A1. Now, what you have to decide is, are those, as it goes up, are my acceleration vectors getting bigger? Are they getting smaller? Or are they staying the same? Okay? That's what you have to decide.
Oh, God.
Huh?
Sorry. Never mind. I thought we weren't supposed to say it out loud and then, like...
Oh, that's cool.
Never
Now,
mind.
look at this in terms of, oddly enough, F equals ma. The only way you can change your acceleration vectors is if you change the force. Okay? So this goes, this Jedi Stoffa. Stop the force and watch. As soon as that card leaves your hand, what's the only force acting on it? Gravity. Okay? Do you know why we don't have a gravity forecast every day? It doesn't change. Okay? As long as you're in the same location on Earth, gravity's pretty much going to stay the same. Now you climb to the top of Mount Everest, hey, it's going to be a little bit smaller. Okay? You go to sea level, you go closer to the center of the Earth, your acceleration due to gravity is going to be a little bit bigger. Okay? But for the most part, it's pretty constant. Okay? So, and that's a good thing. Okay? We have enough things to worry about. We don't need to worry about, oh, what's the strength of gravity today? Oh, man. Okay? That can be one of our spirits day. Oh, it's weak gravity day. Really? Cool. Always jump higher. Okay? No, which would be cool. So that's what you have to decide. And again, when I wrote this lab, I specifically wrote it to make you look at the acceleration due to gravity in 3 different ways. Graphically like this, in terms of a velocity time graph that should look something like this, and mathematically when you go v minus v naught over time. Okay? 3 ways I wanted you to look at this, because here's the situation. Nobody has any trouble what happens on the way up. Oh, it's getting smaller. Oh, slowing down. Velocity vectors are becoming smaller. Positive velocity, negative acceleration. Not a problem there. The problem comes on the way down. You all want to intuitively go, oh, it's speeding up. And we should therefore have positive acceleration because it switched signs. Okay? That was the whole point of this. Okay? Is to force you through this realization that you can have uniform acceleration, you can speed up with negative acceleration as well, but only if you have negative velocity. Okay? That was the whole point of that lab. Okay? Now, on that last question on 25. So, here's what that should look like. Your position time graph is going to look something like this, and your velocity time graph is going to look something like this. And you're supposed to come in here and write down these velocities. So here's how you can tell if you got this problem right. Okay? Ball goes up to a height of 5 meters, which is about twice as the height of the ceiling. So it's a pretty good toss. Here's how you can tell if you got this problem right. Take that velocity and 1 second and find the area of that triangle. Okay? If the area of that triangle is 5 meters, odds are you did it right. Okay? If you find the area of that triangle and it's not 5 meters, I promise you, you did it wrong. Okay? So if you're not sure if you're right, give your paper to your study buddy and go, hey, find the area of my triangle. If that triangle is 5 meters, hey, you like the odds. If it's not 5 meters and they go, that's not 5 meters, I guarantee it's wrong. Okay?
I'm good. Wait, what?
Wait,
Okay.
no, it's fine.
Huh?
No, we have 10.
All right.
What did you say?
Make sure you show your calculations on like 17 through or 16 through 19,
Oh, wait,
whatever that is.
Wait, are we fine?
On the back of page 2, I have to see your calculations because I don't have an answer key because everybody's data is different. Okay? So the only thing I can grade you on is, and so help me, if I see this, let's say I just see that. That's all I get. What does that mean?
I don't know.
I don't know. I have no idea what that means. That has absolutely no meaning to me whatsoever. Okay? That is a freshman level discussion. It means nothing. Okay? Raise the game. This is not about writing down numbers. It is about writing down units so that you can convey to people what that information means. Okay? All right. Any questions on the lab? Dear Lord, Miss Lushaw.
On 14, when you said the inclined plane, I'm kind of confused because if you have a steeper angle, it would go slower up and then faster down. Can you explain, please?
Okay.
Wait, it doesn't?
That's what I'm asking.
Stop silently.
Okay.
Oh. Never mind.
You have 2 different situations. Okay? So what do you want to push them both at the same speed, or do you want to make them go to the same height?
Same.
Okay, we'll push them both. So imagine this. So this is this shallow angle, right? So you're going to push this thing at some velocity, right? And it's going to go to 0, and it's going to go something like that. Let's make up a number. Let's say that took 2 seconds. Just making up a number, okay? So this is for that shallow end, right? Now, if I go to that steeper angle and I push it with that exact same velocity, okay, so it's gonna lead the exact same velocity. Is that line gonna be the exact same slope? Is it gonna take longer to come to a stop, or is it gonna take less time to come to a stop?
Less time.
There's your
That's
answer.
your answer. Okay.
And then realize, what does the slope of your velocity time graph give you?
The acceleration.
Acceleration. Force equals mass times acceleration. So what's the only way you can have a bigger acceleration?
Bigger force.
Because on a steeper inclined plane, gravity is like at gravity external.
Okay.
Does that make sense?
No, it's
Rare that I answer questions from
changing
middle
at a
school
quicker
boys,
rate,
but for you, I
causing
made
the slope to be
it.
steeper.
Yes?
For number 24, the third part on that one, on the first blank, are you asking for like direction or magnitude? Either one would work.
On the velocity time graph,
Number 24.
yeah, the first blank on number 1,
Yeah.
where it says velocity time graph has the same. Huh?
Number 3, the first line.
Oh, okay, I thought you were talking about like the first blank.
Sorry.
Magnitude.
The one, 2, 3. Okay.
So is length fine? Is length okay, or do you want?
Huh?
Is
Length is good.
But
Or length. Okay, are we good?
Yeah.
yes, sir. Yes, sir.
Who is it today?
I don't know because she's not taking the bio test.
She's not taking the bio test.
Yeah, she's skipping.
No, you didn't. No, you
Yeah.
didn't.
She's trying to take it. No, she tested it. But how convenient. Huh? She's not asking. She's like,
No, I'm not telling her.
okay.
I'm not gonna tell her how hard the test is or easy. Look at my hand. I'm not gonna be any good, but
Why are they orange?
because I was testing out this little sample thing,
Self pants?
Self Shannon, and I accidentally rubbed it all over my hands.
The bee's hands?
It was in like a little like
Plastic package.
That's interesting.
this is what it did to me.
Yes. Look, all the way down.
Yeah, don't use that
What's
one.
your initial velocity?
Okay, Saint Tropez.
All the way down.
Saint Tropez.
I've never heard of
Saint Tropez?
It
Tropez.
doesn't seem like it's a Target brand.
I got it.
Saint Tropez?
Yeah, that one. The one you used.
I love it. No, I'm not. Because
Everyone deserves a fair chance in this
I
world.
don't get a choice. I would take it today if I could.
no, you wouldn't.
Yes, I would.
No, you wouldn't.
You have your breath.
Yeah,
It's your breath.
yeah. You can
Oh, you have a breath too?
I'll tell you all of the questions. I'll take pictures.
I'll
of
tell
it
you
for
all the.
Oh, that's so
yeah.
nice. Thank you. I appreciate it.
I know. But that's,
Let's see if I have a long hair.
What is that? What is it? I don't know. I can't tell.
I don't know. It could be. That might be a spider bite or something. It's okay. Oh yeah, I have furniture on my deck now too, so you can come and sit on my furniture. We don't have furniture in our actual house yet though, so. Although we did finally get bathroom mirrors, so now you can like look in the mirror. Yeah. Wanna come over Saturday night?
Saturday.
Both.
We have practice and a tournament.
I know, so Saturday. We have a tournament on Sunday too.
Saturday.
Yeah, I know, so Saturday night.
Tucker wants my fat head for Saturday, so you're gonna come or just give it to me.
Oh, I have to work. I'll just give it to you. Trigger, he remembers it. Oops. I still have Carson's poster still in my car, so I kind of like want to get it back.
Maybe with physics
the poster?
Mr. Burkham, I think I'm gonna be going for the physics test for Topeka. He hasn't told us yet, but I'm pretty sure I'm going. So can I take it on Wednesday?
Tell her no. Tell her to take it a day early.
Take it Monday.
I'm gonna go on
If
Monday.
you ever have to miss for college, you can say
Yeah.
No, we never have to miss.
so.
You never miss though. So,
I've never
can I take it on Monday? Because I have to work.
This is the one where we go to Topeka.
Is this the really big test?
You skipped the last test, so you don't deserve it.
I was sick.
So yes, he's
No, I'm just gonna try and switch.
What?
I hate this.
Balls, I
like
know.
sweet tea?
I don't miss anything for soccer, but for tennis, I miss a bunch of classes.
I don't like sweet tea, but like, I hate unsweet tea.
Tennis courts have teams.
Oh, I've been recording
It's hard to
this.
play. Some of them do.
Okay, so today is a good news, bad news day.
Oh.
So I'm going to talk. You don't have any homework.
Why just like what's wrong?
Not going to the gun show? You can. You better give me discount tickets.
What if I
Okay.
I gotta work on my gum.
No more ripping shirts.
No.
Not again.
Not no.
That was kind of funny though.
I had such a bad visual with that. I'm going to have to go to therapy. Stop. Okay. Okay. So there we go. So what we're going to do today is we're going to go through the first 4 equations that are on your Big Dog equation sheet. And the reason that I'm basically willing to sacrifice a day is that you have to understand where these equations are derived, what the basis of this are, and then it makes sense. Because if I just turn you loose with the problem and go, oh, here's an equation, pick one, it's going to be a train wreck, okay? So as we go through these, I'm going to show you a couple of things. Number one, how I always work them, okay? The process that I go through. Then I'm also going to try and get you to look at these problems from different perspectives. Because the more ways you can look at a problem, the better off you're going to be. So I give you this equation sheet, but here's the dichotomy. The worst thing that you can do when you get these problems is to immediately go, oh, which equation am I going to choose? Okay? The test is going to be a train wreck. Okay? You're not going to get it. You have to be able to think your way through these problems. Now, the beauty of every acceleration problem is that every acceleration problem you're going to have can only go one of two ways. What are the only two things I can do in any acceleration problem? Make you speed up or make you go down. That's the first thing you need to decide. Read the problem. Hey, what's the car doing? Slowing down. Okay. If it has positive velocity, it has to have negative acceleration. Okay, cool. If the car is speeding up and you have negative velocity, you have to have negative acceleration. Seriously, start with that idea. Because every problem is going to play out that way. The other thing is that if you, and some people like this, so you, on all of these problems, you only have at most 5 variables, okay? Your final velocity, your initial velocity, your displacement, your acceleration, and your time. So what some people like to do, and this is a personal preference thing, as soon as they get a problem, they're going to write down, it's kind of New Orleans thing, they're going to write down the double VDAC, okay? Your 2 velocities, your distance, your acceleration, and your time. Okay? That's it. Now, the beauty of this test coming up, which is a week from today, this will be the first really, really big test. The beauty of this test is that you only have 4 potential equations. Okay, that's it. There's only, it is a 4-trick pony. You just have to figure out which equation that you're going to use. But before you can decide that, you have to look at it in terms of going, well, what am I given? What's happening? Which equation, which variables do I have? Which ones do I need to worry about? Which ones do I not need to worry about? Okay? So, if you look at this very first equation, V equals V naught plus AT. So, all this is, in a weird way, is the slope-intercept form of y equals mx plus b. Okay, that's it. It is a slope-intercept form. It doesn't look anything like it necessarily, but it is. It's a slope-intercept form. So this is relating to any velocity time graph. Okay, so let's maybe say you're starting off here at 10 meters per second, and you're going to end up at 20 meters per second. And you know that's going to take you 2 seconds, and you want to figure out what's the acceleration. Okay? So here's what you want to think through. When you see V, okay, all this, that V is nothing more than the y value. Okay, that's it. It's a y value. Time, that's your x value, because that's what's graphed on the x-axis. That's why we always put time along that x-axis. Your initial velocity, that's your y-intercept, okay? So literally, all this is a slope-intercept form, okay? If you keep that in mind, think, oh, okay. Now, the other thing that you have to remember, listen to me very carefully. Acceleration is not how fast you go. Acceleration is the rate at which your velocity changes, okay? Cannot emphasize this enough. Acceleration is not how fast you go. So, how does acceleration play into any velocity time graph? It's your slope. Oh, that's kind of cool, right? So this slope, right? Slope is that acceleration. Okay? So in this situation, here's how this would play out. You would say, I'm a much better physics teacher than I am artist. So here's the carrot car. Okay? It's a generic thing. Just the carrot car. So I'm telling you that the carrot car is moving at 10 meters per second. At some point later, the carrot car is going to be moving at 20 meters per second. So just start with this idea. Jackering. Did the carrot car speed up or did the carrot car slow down? Sped up. What was the sign of my velocity? Positive or negative?
Positive.
So what sign does my acceleration have to be?
Positive.
Okay, so right away, and I know before I do anything else, if I get a negative acceleration, I've done something wrong. Okay? Because I know I have positive velocity, I'm speeding up, I have to have positive acceleration. Okay, so start with that idea. So all I'm asking you to do is basically find the slope of this line. If you're in a math class, basically what I've done is that I've given you 2 coordinate pairs. I've given you 0 seconds and 10, and I've given you 2 and 20. If you're in a math class, this is how this problem would play out. I would give you 2 x and y coordinates. 0, 10, 2, 20, and I would say find the slope. And you would go, oh, that's change in y over change in x. Okay? That's what you all would do in a math class. And you would write down a number and it wouldn't have any meaning. You just write down a number. What we're going to do, the mechanics of this are going to be the exact same. It's the exact same mechanics. We're going to say change in y over change in x. But we're going to call that change in velocity over time. And that's going to get us acceleration. But the mechanics are the exact same. Now it just has a physical meaning in terms of, oh, this is what the car is doing. So the other way that you can look at this is in terms of velocity vectors. So this thing has a certain velocity vector, 10 meters per second, okay? Later on, what's going to happen to that velocity vector? Bigger, smaller, stay the same? Bigger. So over here, I'm going to have up to 20 meters per second. So which direction are my acceleration vectors going to point? Same direction, opposite direction?
Same.
Same direction. So my acceleration vectors are going to be pointing in that direction. So when I ask you to draw motion diagrams, this is what I'm talking about. Draw me some velocity vectors. And again, you only have one of two options when you draw your velocity vectors. Make them get bigger, make them get smaller. If your velocity vectors get bigger, put your acceleration vectors in the same direction. If your velocity vectors get smaller, put your acceleration vectors in the opposite direction. That's all you have to do. Okay? That's it. It is a two-trick pony. That's it. Bigger, smaller. Speed up, slow down. That's it. Now, if you like the variable option, and again, you don't have to, I'm just pointing this out because some people like this. Okay, so in this situation, my initial velocity is 10 meters per second. My final velocity is 20 meters per second. Distance, that's not part of the story at this point. Okay, I don't care about the distance. My acceleration is what I don't know, and I know my time is 2 seconds. Now at this point, I've looked at this problem from a whole bunch of different perspectives. I've looked at it from a vector standpoint. Oh, my velocity vectors are getting bigger, and they're positive, therefore I have to have positive acceleration. I've looked at it from a graph perspective and said, oh, here's the velocity time graph. I'm starting at 10 meters per second, I'm going to 20, that's going to take 2 seconds. I'm trying to find the slope of the line. I've looked at it from a variable equation and said, okay, hey, here are the variables that I have. I know my initial, my final, I don't care about distance, my acceleration is my unknown variable, I'm trying to find time. Okay, now I have the picture. Okay, car speeding up, got to have positive acceleration, slope of the line positive coming up like that, I know my initial velocity, my final velocity, I'm trying to find the slope of the line. I've analyzed this thing completely. Now, I always do a three-step process. And if you look at my answer keys, and I've been doing these longer than you all have even thought about being on this earth. And if you look at my answer keys, I work these problems in 3 steps. And they're always the same 3 steps. And there's no variation on the theme. The first thing I do is I write down, what equation am I going to start with? Okay, that's the first thing I'm going to decide. You only have 4, okay? That's it. You only have 4 potential equations, right? So in this case, I'm going to go, oh, I'm going to choose V equals V naught plus AT, right? I don't want to write down distance because that's not part of the story. I know my initial velocity, my final velocity, my time. I don't know my acceleration. So that's the first thing I'm going to do. I'm going to write down that equation. Because when you work these problems, and I grade them, you have to get out of this mindset that says, I got an answer. It's a horrible method to have, okay? Focus on the process. If you do the process right, the product, the answer will take care of itself. Unfortunately, for the past 11 years of your education, you all have been taught to focus on the answer. Did you pick C? Okay? Could you go on a computer program and type in 12? Okay? That's it. And that's what I find disturbing, is that we're shifting more towards, can you write down answers and not worry about conveying that information. So I'm old school, okay? But it works. And if there was a better method, if I thought, hey, here's a better way to do this, I'd embrace that. But I haven't found anything better, because it works. So I'm going to start with this equation. What I'm telling you all, this is what I'm going to, this is the beginning of this journey. Okay? I'm going to start with this equation. The next thing I have to decide is that, do I need to solve that equation for one of my variables? So I need to get acceleration by itself. That's what I have to do, right? So, Eli, how am I going to get acceleration by itself? What am I going to do?
Subtract by velocity initial,
Okay?
and then divide by time.
I like that. Okay. Now what that does is that sets the stage. Okay? Here's what I'm going to solve this equation for. And I promise you, every problem we're going to work between now and December 20 whatever, this is the process I'm going to go through. I'm going to write down the equation, I'm going to solve it. The last thing I'm going to do is put in the numbers, okay? Because the numbers are just the end of the story, okay? You all want to jump to the end of the story and skip like the first 3 chapters, okay? You want to get straight to whodunit, okay? It's a train wreck. You gotta read the chapters of the book to get to the story, okay? Now, then I can put in my numbers, okay? Now I'm to that point. So I'm going to come in here and go, okay, my final velocity, that's 20 meters per second, minus 10 meters per second, and my time is 2 seconds. So, miracle of miracles, I get 20 minus 10 should be 10 divided by 2. That gets me 5 meters per second squared. Okay? And again, embrace this idea of units. Okay? Just don't randomly write down numbers and hope, oh, a miracle happens. I'll get acceleration, because that's what Bergkamp asked for. Okay? In an ideal world, you all would end up with, oh, I'm going to look at what the units are. Oh, that's meters per second times 1 over seconds. I'm going to get meters per second squared. In an ideal world, if I were king for a day, you all would do the units first and then go, hey, I'm going to get an acceleration. And then you'd read the problem and go, what does Bergkamp want me to find? Oh, Bergkamp wants me to find acceleration, winner, winner, chicken dinner, okay? As opposed to crunching numbers into a calculator, the oracle speaks to you, the oracle says the answer is 5, and then you read the question and go, oh, what is Bergkamp looking for? Oh, he wants acceleration. I'll put meters per second squared on the end, okay? So if you really want to understand this process, figure out what units you get, knock on the door of the problem and go, hey, I'm here with units of acceleration. Then open up the door and then go, oh, Bergkamp wants acceleration. That's cool, because that's what I'm going to get, okay? As opposed to, on the other side of the door, you get a number, and then you go, Bergkamp wants acceleration. Oh, I'll put meters per second squared on the end of it. If you can embrace this idea of paying attention to the units and getting those first, you're going to be a lot better off. Now, here's what this number means, okay? 5 meters per second squared. What that number means is this. You're starting at 10 meters per second, okay? That's the slope of this line. Let me draw that a little bit bigger, because that's getting all screwed up. So there's 10 meters per second. There's 20 meters per second. And there's 2 seconds. We've got a line like this. So the slope of that line is 5 meters per second squared. Now, here's the $1 million question. At the end of 1 second, how fast are you going?
No, 15.
Why? Your answer is right.
Because 5 meters per second is the A, which is also the X, or no, the slope. And then you take that times X, which is your time, and then that equals Y. But you also have to add that to the Y-intercept, which is 10.
Okay, you gave a beautiful mathematical answer.
But
Okay?
according to the equation, yeah.
Okay. So Morella went through a whole beautiful mathematical explanation. She goes, the y-intercept is 10, your slope is 5 meters per second squared. I take 5 meters per second squared times 1 second, I get 5. I add that to the y-intercept, I get 15. Okay, and that is a beautiful mathematical operation. Answer. Spot on, perfect.
Thanks.
Okay? Now, somebody give me the physics side of it. How fast are you going to start with?
10
You're going 10 meters per second, right? What does that acceleration mean? Every second that goes by, what happens?
Velocity increases.
My velocity increases by 5 meters per second. I'm starting at 10, 1 second goes by, I gain 5, where do I end up? 15. At the end of 2 seconds, I'm going to gain another 5, I'm going to end up at 20. Okay? So, that's why I said you have to understand acceleration is not how fast you're going. It's the rate at which your velocity changes, okay? So, what this means is that if I'm going 10 meters per second, every second that goes by, my velocity increases by 5 meters per second. That's what the number means, okay? Now, let's change it up a little bit. Car is moving at 20 meters per second. And at some point later, time of 2 seconds, the car is going at 10 meters per second. Now I want to calculate the acceleration. So it's the only thing that's going to change.
Acceleration. Is gonna
Okay.
change, yeah.
So if you look at V naught, dat, okay? I'm still not worried about my distance. That isn't part of the story. But now, what's the difference? Now what's my V naught?
It's
20 meters per second.
20,
What's my final velocity?
10.
My acceleration is still what I don't know. My time is still... So on my velocity time graph, I'm going to start at 20. Where am I going to end up?
10.
So right away, am I speeding up or slowing down? So what do I know my sign of my acceleration has to be?
Negative.
Has to be a negative value, okay? So this car is starting with some positive velocity, and it's slowing down to 10 meters per second. So right away, I have positive velocity, and I'm slowing down. I have to end up with negative acceleration, okay? So then, again, if you go through that process, solve for that acceleration, V minus V naught over time. Now, here's where the magic happens, really. It's magic. But I'm going to take 10, which is my final velocity, minus 20, and divide that by 2 seconds, and I'm going to get negative 5 meters per second squared, okay? Numerically, it's pretty much the same, but it has two completely different meanings. That positive velocity on the first one, going from 10 to 20, I was speeding up. Oh, I had to have positive acceleration. This one, I still have positive velocity, but I'm slowing down, so now I'm going to have negative acceleration. Okay? So it's all this is literally is a slope-intercept form. Okay? That's all it is. People flip out and go, oh, it's a physics equation, V equals V naught plus AT. It's slope-intercept. That's all it is. This is why we're always going to assume that we have uniform acceleration. Because if you don't have uniform acceleration, that means that line is not a straight sloping line. Which means if your acceleration is changing, then it's like, well, which acceleration do I find? Because if it's a curved line on a velocity time graph, the slope isn't constant, therefore your acceleration isn't constant because your force isn't constant. So this is why, listen to me, every velocity time graph that you're going to draw is going to have some form of a straight sloping line. Now, we might change the slope, we might go from here to here, but whenever you are drawing a line on a velocity time graph, you will never draw a curved line on a velocity time graph in this unit. That's not going to happen. It's always going to be uniform acceleration. It might be positive, it might be negative, it might be zero, but you were always going to draw a straight sloping line on a velocity time graph. Okay, no exceptions whatsoever. Okay, stop that. Stand up. We need to come up with the second equation. Okay? So, some people kind of flip out on a problem like this. So, all I'm telling you is that some object is moving with some V naught. Maybe it's a mouse, a squirrel, a penguin, whatever. Okay? It has some initial velocity. It's going to speed up to some final velocity V over some amount of time. Okay? And what I want to do is figure out how far this thing is going to go during this accelerated motion. Okay? So, how does that play out if you want to find a displacement? How can you use a velocity time graph to find the displacement?
Area.
Area. Okay?
Yeah.
Yeah, so what, because this is awkward, right? It's like, so what we're going to do is going to break this up into two different areas, okay? we're gonna break it up into this lower area, and then we're gonna break it up into this upper area, okay? And then what are we gonna do when we get the two areas? Add them together, okay? So, how am I gonna find that lower area? What am I gonna do? It's a rectangle, so area 1 is gonna equal what? V naught times time, right? And you're going, oh, it's a rectangle with length times width. And it is. The width of this triangle is time, and the height of that triangle is V naught. Okay? So, if I take V naught times time, that's going to give me that rectangle. Cool with this? Okay? Now, that upper area looks like a, I define the area of a triangle. 1/2 base times height. My base is going to be time. But what's my height going to be?
V naught minus V, or V minus V naught.
Oh, there's a big difference.
Well, V minus V naught, yes.
Why?
Because that's just what you do.
Because that's just what you do.
It makes sense.
It does. Well, look at it this way. What if this was 5 meters per second? And let's say that was 20 meters per second. What would the height of that rectangle be? 20
Or
minus
the triangle.
the triangle.
Oh,
Because what would
15.
the height of the triangle be?
15 meters.
15, right? Because you take 20 minus,
5.
and you get 15. So, the area of that triangle, area 2, is going to be 1/2 my base, which is time. And then the height is going to be V minus V naught. Cool with that?
Very cool.
So now, my total area, is going to be area 1 plus, as opposed to area 51, which is something completely different. So that's going to be V naught T plus 1/2 time times V minus V naught. Now, this, at this point, is so non-elegant. And what you see is that there are certain equations that have a certain elegance to them. This does not, okay? But we can get to that point. So what I want to do is I want to distribute this 1/2 time, okay? So I'm going to have V naught T plus 1/2 VT minus 1/2 V naught T. Now, can I combine any terms?
V naught T.
So if I take V naught, 2V naught or 2V naught? That is the question. So if I take my V naught and add that to negative 1/2 V naught, I get, so I get 1/2 V naught T plus 1/2 VT.
Beautiful.
Now, we're going to do a little factoring out. We're going to write this as 1/2 V naught plus V times time. Okay? So that's going to get me some displacement. All right? Huh? Oh, no, there's not, it's not quadratic, because nothing's squared. Oh, kind of. Okay, now, let me explain how this works. Pretend that that equation doesn't exist. Okay? If I ask you to find the average of two numbers, like let's say 2 of you took a quiz. One of you got 8 out of 10, the other one got 10 out of 10. How would you find the average of the two scores? Add them together, divide by 2, right? So when I take V naught plus V and divide by 2, what am I finding?
Average.
I'm finding an average velocity. Okay? That's all I'm doing, is just finding an average velocity. Okay? So don't flip out and go, oh, where does that 1/2 come from? It's an average velocity of two values. Okay? That's all it is. It's just an average velocity. So here's how this would play out. Let's go back to the carrot card. So Here's yonder carrot car. It was moving at 10 meters per second. It's going to speed up to 20 meters per second, and that's going to take 2 seconds. And I want to figure out how far we're going to go. Okay? Now, at this point, and this would be a word problem. I would say the car is moving at 10 meters per second. It's going to accelerate at 20 meters per second. It's going to travel 2 seconds. How far will the car travel during this time? Okay, so that's how it's going to play out. All of these are going to be word problems. Okay, so if you hate word problems, ooh, it's not going to end well. Okay, let me give you a hint. Life is a word problem. Okay, just solve it. So, if you like the V naught dat thing, okay, so V naught dat. So now my final velocity is going to be 20. That's 10. I don't care about my acceleration. My distance is my question mark. My time is 2 seconds. Now, here's what you all are tempted to do. This is what you're tempted to do. I highly recommend that you not do this, because I'll have an aneurysm. What you're tempted to do is go, oh, it's going 10 meters per second, 2 seconds. I'm going to take 10 times 2, and I'm going to get 20. The car went 20 meters. Physics is easy.
It's beautiful math.
Okay? That would be such a train wreck. Because what you're trying to do is that you're trying to use distance equals velocity times time. What's the only time you can use distance equals velocity times time? Constant velocity. Guess what unit we're on?
Acceleration.
We're on acceleration. Acceleration means your velocity is
Changing.
So if you find yourself trying to use that, have an intervention. Okay, call a friend going, I'm addicted to distance equals velocity times time. I need help. Okay, call me. We'll have an exorcism. Get a Ouija board or something. Okay, actually we won't. I hate that kind of thing. But don't. Oh, Halloween! Don't even get me started.
You don't like Halloween?
Oh, I hate it with passion.
I love Halloween.
Oh, I hate it with passion. Hate Halloween.
What did Halloween do to you?
Yeah.
Funny shit. I was probably 4 or 5 years old. I can tell you the exact details. Okay. 4 or 5 years old. I grew up out in Cheney, Kansas, in like 6th grade. And there was Dewey's IGA grocery store at the end in the south end of town. There's 2 grocery stores, one on the north end, one on the south. I was with Mom. We were shopping at the one on the south end of town, and it was like middle of October. And we started on I can tell you exactly how this thing played out. We started on the south end of the store, because that's where the produce was. So Mom always started in the south end, and she would weave her way through the aisles, okay? About 3/4 of the way across, we were like headed east. Make the corn, head west. Around this corner. They had this full-size black witch hanging from the ceiling, riding on a broom, black hat, black cape, green face, this big hooked green nose with the wart on the end of it. I flipped shit. Okay, that was honest to God, I did. I started screaming. I was like, Mom could not, I was like, literally, I was out, gone. Okay? It was like, Mom had to like literally leave the grocery store. Had to come back later and pay for the groceries and pick them stuff. I got to get my son out of here. I completely flipped out, and I have hated Halloween ever since. Okay? It's like, no, go trick or treating. No. Okay, dress up. No. Okay? Let's go to a haunted house. Hell no. So that's what Halloween did to me. Okay?
That would be a good fundraiser thing.
No.
You know, go to Field of Screams if you get your goal.
Nope.
That'd be funny.
Nope. There is not enough money. There is not. It would take a lot of money. It would take a lot of money to get me to go. We can't even negotiate that price at this point. Okay, it's going to be more than the tattoo cost. Let's put it that way. Okay. Yeah.
Oh yeah, do you guys know about the tattoo?
Oh.
Are you doing another fundraiser this year?
I don't know.
We should. You should. Yeah. Yeah.
I'm
He
not
dyed his
dyeing,
hair
I'm
red
not
and
dyeing my
green
hair again either.
last year.
That has sailed. Okay. So, here's the deal. Here's what you cannot do in this situation. I just can't take 10 meters per second and multiply that by 2 and say it went 20 meters. Because you don't have constant velocity. Okay? So, here's what you're going to do. If you look at this on a velocity time graph, come on, seriously, okay? You're starting here at 10 meters per second. You're going to 20, and that's 2 seconds. So basically, this equation looks horribly complicated, but if you think about it, all you're doing is that I'm finding the average of 2 velocities. So what's the average between 10 and 20?
15.
15. So what I'm saying is that on average, I'm going 15 meters per second. On average, I'm going 15 meters per second. For 2 seconds, I take 15 times 2, I get 30. Okay? So if you're an average, not average in terms of like behavior or personality, if you're an average kind of person in terms of the mathematical concept, I'm finding the average between 2 numbers, 10 and 20. Oh, that's 15. So on average, I'm going 15 meters per second. For 2 seconds, I'm going to travel 30 meters. You go, oh, Mr. Burkamp, I'm an equations kind of person. I was president of the equations club. Good for you. Okay? So we have this to the rescue. V plus V naught times time. So you got 1/2 times 20 meters per second plus 10 meters per second times 2 seconds. 20 plus 10 gets you 30 divided by 2 is 15. 15 times 2 is 30 meters. Okay? Now you go, oh, but Mr. Burkamp, I just love finding areas of shapes. I was like president of the area club in high school. That would look good on a resume. So, you could go to this and treat this as 2 things. You could take 10 times 2 and get 20 and find the lower area. You could find the area of that triangle up there, add the 2 numbers together, you're still going to get the exact same answer. Okay? I don't care. It makes me no difference whatsoever. Now, an interesting thing happens on the way to the physics equation. Let's say that you're going to travel at 20 meters per second at a constant velocity for 2 seconds. Could I still use distance equals 1/2 v plus v naught time? Could I still use that equation even if I have constant velocity?
Yeah.
Yes, because what's my initial velocity going to be? 20. What's my final velocity going to be?
20.
20 plus 20 is? Half of 40 is? 20. 20 times 2 gets me 40 meters. Okay? Now, the other thing that you can do is go, oh, Mr. Burkamp, you went 20 meters per second for 2 seconds. You're going to travel 40 meters. So here's the deal. This distance equals 1/2 v plus v naught time works under any circumstance. It works if you're speeding up. It works if you're slowing down. It even works if you have constant velocity. I know that sounds like an infomercial, but wait, there's more. You can speed it up, slow it down, and for next to $9.99 for shipping and handling, you can use this for constant velocity as well. Okay? It slices and dices at Julienne. So, you can use this under any circumstance. Now, distance equals velocity times time. It's a one-trick pony. What's that one trick? The constant velocity. Okay? So that's why it's a cool equation, but you have to be very, very careful about how you use it. Okay? So the distance equals 1/2 v plus v naught time. You can use that all the time. Okay? So, got that. Now, we need to do a little bit of hocus pocus, which is not related to Halloween. Let's get that straight right now. So, what we said is that we had V equals V naught plus AT. Cool with that? Got that one. We just came up with distance equals 1/2 V plus V naught time. It's the second equation. Now, we're going to merge these together. What I'm going to do is I'm going to take V naught plus AT, and I'm going to go in here and I'm going to substitute that into that. Okay? Merge these together. Okay? So I'm going to have distance equals 1/2 V naught T, or V naught plus AT, then plus V naught, and all of that times time. Okay? So, at this point, this is this huge monstrosity of an equation that has no beauty whatsoever. Okay? But we can combine some terms. So, can I take V naught and add that to V naught?
Yep.
I can V naught, and then if I do combine those, I get I2 V naught. Plus AT gets times time. Now, we're going to do this without a safety net, but we can handle this. I want to do a double distribution at the same time.
Oh my gosh.
Stunning. I want to distribute the 1/2 at the exact same time I distribute the time from the other side. So I'm going to distribute the 1/2, I want to distribute the time. Nick, what am I going to get? This is without a safety net. Come on, you're on the tightrope.
V naught plus.
Oh, right away, people are going, oh, you're going to fall, stop.
Oh, V naught T plus 1/2 AT squared.
Ah. Whoa. Whoa. There's a slap. There you go. So I got 1/2 AT squared plus V naught time. Okay? So this is the other equation. So what I did is I took the slope-intercept equation, I took the average velocity equation, and I merged them together and got this. Okay? So look at this from a unit's perspective. I want to end up in distance, right? So I've got 1/2 AT squared. But what's acceleration going to be measured in? Meters per second squared. Time's going to be in, but that's going to get,
Canceled out.
so I'm going to get meters. Then I'm going to have meters per second times, seconds cancel out, I get, can I add meters to get meters?
Yes.
Yeah, if we can't, we're really screwed. Okay? All right? So it works in terms of units. So now, we're going to do a little comparison of the three equations. So we got V equals V naught plus AT. We have distance equals 1/2 V plus V naught times time. And then distance equals 1/2 AT squared plus V naught time. Okay? So two of them involve distance.
Okay.
One involves acceleration. The other one doesn't involve acceleration. So here's how this would play out. You would say, all right, here's Joe Carrot Car. Topher, pick a number between 1 and 5.
3.
So the car is going to accelerate at 3 meters per second squared. Zach, pick a number between 5 and 10.
9.
Ooh, living on the edge. So the car is going 9 meters per second. And Dime, pick a number between 20 and 25.
24.
Okay. So, and Morella, pick a number between 5 and 10.
9.
No, don't pick
I
9.
mean, 6.
Okay, 6 seconds.
That's a horrible number.
So, here's how this would play out. Okay? So, you're designing a road, okay? And you know, cars, when they merge off the highway, they're going to, this is like an acceleration lane. Cars are going about 9 meters per second. you know when they merge onto the highway, they're going 24 meters per second. Typically, that's going to take them about 6 seconds, and cars will average an acceleration of 3 meters per second squared. So what I have to figure out is that how, if I have these parameters, how long do I need to build this section of road to allow this to happen? Okay, that's how this would play out. It's like, okay, how long does the road have to be? If these are the parameters, this is what cars are going to do, I need to know how long to build this section of road. Okay? Now, in this case, we're going to look at V naught, dat, right? So, my final velocity, let's get that up. My final velocity is
24.
24 meters per second. Oh, come on, change. My V naught is 9 meters per second. My distance is
Question
what I don't know. My acceleration is,
3 meters per second.
and my time is
6 seconds.
6 seconds. Okay? So there's a couple of ways we can do this, depending upon your preference. One option is that you go, well, we just came up with that really cool equation that distance equals 1/2 AT squared plus V naught time. Okay? Do I know my acceleration?
Yep.
Do I know my time?
Yep.
Do I know my initial velocity? Yep. So I don't have to solve it for anything. I can just plug this in. So this is going to be 1/2 times my acceleration of 3 meters per second squared. My time is
36 seconds squared.
plus, and then my V naught is 9 meters per second, and then my time is 6 seconds. Okay? Now, here's what you're going to do wrong on this equation. You mark my words, this is what you're going to do wrong. You are going to forget to square that time. Okay? That's what you're going to do wrong. I swear to you. And you all sit there and go, I swear to you, don't do that. Lie. Okay? Lie. That's what you're going to do wrong. Or you forget to multiply by 1/2. Most commonly, you forget to multiply, you forget to square it because it's like on the end. Okay? And you do everything else. So, what do you get out of that? 54 plus a lot. What do you get?
108.
108 meters?
That's what I got.
Okay? So that's about the length of a football field. Okay? So if I'm building this acceleration lane, I'd have to plan on building a road about the length of a football field. Now, is there another way that I could get this distance, knowing what I know?
Yes, the 1/2 V naught being.
Yeah, I could use distance equals 1/2 times time, right? So I'd have 1/2 times, what were the numbers? 24 and 9. 24 meters per second plus 9 meters per second times a time of 2 seconds. No, 6 seconds. My bad. That's a huge difference. Six seconds. So out of that, you get hopefully 108 meters. If I don't, something's wrong. Okay? So I don't care how you do, which one you choose. And that information you can choose either method. You're going to get the same answer. Now, here's the $1 million question. Can I use this equation even if I have constant velocity? Well, yeah, if I have constant velocity, what's my acceleration?
Yes.
I don't have any.
No
If I'm at constant
acceleration.
velocity, I don't have any acceleration, right?
Yeah.
Right.
If I don't have any acceleration, guess what? You get distance equals velocity times time.
Yes.
So you can use this both with accelerated motion and with Constant velocity. Maggie?
The second one gives you a different answer.
Yeah, it does. That's what I was about to say too.
I just,
My
Oh
bad.
no.
I got trust in you on.
Let's see.
Well, somebody did something wrong, because they both have to give you the same answer.
What?
I know they might not, because I randomly picked these numbers. And so that final velocity is gonna be different, because if you take 3 meters per second times 6, that would actually be 18.
Nope,
Yeah.
Zach, you're right. It's 54.
Okay, if you change that to 18, then you're gonna get the same answer. I
They're
randomly
different.
have people give me numbers, and that acceleration and that initial velocity at that time won't produce 24.
Oh, okay.
Okay, I had people randomly give me a final velocity, but if you have that acceleration of 3 meters per second squared, and if you take 3 times 6, that gets you 18. If you take 18 plus 9, you get like 27.
That should be 5, if it was 5 seconds.
Yeah, that's, I just randomly pick numbers. Okay, that's where that went south. Okay,
Sure.
I am done. You have no homework?
Yay.
So tonight or tomorrow, we will take this up. Tomorrow, though, you get your first real physics assignment.
The stuff we've been doing hasn't been
No.
real? Huh?